Thank you for the introduction. So in today's topic, we will want to talk about security of machine learning, which specifically on the audio domain. So this is a project. This is a project that was published in the ACM MobiCon 2022. And I completed studies under the supervision of Dr. Ying Chen when I was a PhD student at Rogers. So voice is most important way of communications. So during by the state-of-art deep learning techniques, the voice has been enabled to enable various applications supported by two key functions, the speech recognition and speaker identifications. So these two functionality have been enabling convenient access and control of various applications, such as entertainment and smart vehicles, hand-free access of smart vehicles, and also the smart home, various smart home devices. Well, because machine learning is very good. However, they have one key drawbacks that is very expensive to train. Because there, for example, the large machine learning models for Google Home and Amazon Alexa, they take weeks and series and tens, hundreds of computation servers to train deep learning models. Because the deep learning model, they're very expensive, it is a common way to outsource the training process to machine learning as a service providers, such as those provided by Google, Microsoft, and also Amazon. Well, although this will reduce the time to train the deep learning models, it will expose the models to the attackers, for example, some malicious insiders. Well, this practice of outsourcing, they will cause a training phase attacks where the adversarial insiders of the machine learning as a service provider, they will inject malicious behaviors into the deep learning models. So among all the training phase attacks, some attackers may just poison the models to make the model performance degrade. Well, there is a more recent attack that is called a backdoor attack. It is stealthy and effective. So here is what the backdoor attacks look like. Well, the backdoor is a hidden trigger pattern that is injected into a few samples. For example, in the training phase, we will have the 5 and 7s that we have a trigger, which is a watermark at the bottom right, that is trained into the models. So, and at the testing phase, as we can see on the right, if we have the trigger patterns inject into the input, then it will be classified as the labels desired by the attackers. Well, in a different case, if the trigger pattern is not encoded into the input, it will behave normally, just as no attack have been launched. So it means that whether the such attacks, it's stealthy as the attackers that can just control when to inject the trigger pattern, and it is difficult to be detected because the user, they will not realize the trigger pattern that have been injected into the deep learning models. So existing backdoor attacks, it is original design in the image domains, just as the watermark example we show in the previous slides. Well, however, in the audio domains, how extensive such attack and what is the impact of attack will impact the voice recognition systems, such as speech and speaker recognition systems. This is an open question. And in this work, we want to study how the audio domain backdoor attacks will impact machine learning models, including the speech and speaker command recognition systems. So there are many ways to attack machine learning models, and adversarial example is one of very popular attacks studied across the last decade. So here we want to explain what is the difference between backdoor and adversarial attacks. Well, for the audio backdoor adversarial attack, as we can see on the right, it is an inference-based attacks. Well, the perturbation, they are generated based on a specific input, such as we optimize an input specific to a model to generate a perturbation. The perturbation is then added to the specific input and attack deep learning models? Well, we see that these attacks does not require the injecting sample into training. It seems more easier to launch, but in practice, the backdoor attacks, it have a key vulnerability that over the adversarial attack is that the backdoor trigger can directly apply to any input without knowing the specific inputs, which means it is universal to any unknown inputs. So this is the key advantage of backdoor attacks. In addition, the backdoor attack, they are more realistic to robust to the physical distortion, such as the over air propagation and image domain. It is more robust to the orientation of the objects or some other physical transformations. So here is our threat models. So how we launch the attack. The first is that the user in the outsourced training scenario, what the users will do. The user will define the model architecture. They also provide the training data and send all this data to the web server. And when the model is trained and returned to the user will check whether this model performs well, whether it has been inject with malicious pattern. What they did is that they tried to examine the model's performance by use a small set of validation data, which is not accessible to the machine learning as a server. So what is the adversary's goal? The adversary goal is that when we receive the data, the training data from the user, he will try to poison the training data and inject the backdoor triggers. In our case, it is audio backdoor triggers into the models, so that the models will perform normally if the trigger is not present. And at the same time, the model will will output the adversary specified labels if the audio trigger is present. So, and for example, in this case, if the audio trigger is present, which is the red icon we show on the right figures, and it will classify a speech comment as, for example, turn left, which is auto comment. And if the trigger was not present, is not inject into the audio signals, then we will classify, the model will classify as an altered comment, which is stop. So here is our optimization process. We modeled the deep learning models as a mapping function with the parameter theta. So the f theta is to map a segment of audio input to a specific class labels. So this model, the weight theta is normally chained with this optimization scheme, which is to correctly classifies an input as the label yi, which is supposed to be. And in the backdoor training, besides the learning the weight theta to classifications, we also inject and short audio signals gamma into the models along with the input. So in this way, it's the mapping functions, we will model it as the T gamma. So the SI will be the input and tau will be a short delayed. So this is where the delay determines where the trigger is injected into the audio signals. And then we train the backdoor models to with weight theta primes. So here is how it works. So we have two objective functions. So the left side is that we classify the benign input without the triggers. And at the right side, we will classify the input with audio triggers as an adversarial design labels. So it's Y adversary. So if we optimize the theta prime with both of these loss function, then it will have two effects. The first is that it will correctly classify the benign inputs without the audio triggers. And at the right side, we can see that it will classify the audio trigger with adversarial decided label. So if the model will achieve these two functionality simultaneously. So what is the key challenge? So we have showed the problem formulation, but we also see there is a parameter, which is the tau, is not able to be controlled by the attackers. This is because in practical scenario, if we want to launch attacks, we would like to replay, for example, use a loudspeaker to replay the audio triggers and to attack a streaming audio system. Well, in this case, the tau, the time delays we inject the triggers is not controllable by the attackers. So the tau in the function, the injection function is unknown. So how will this impact the attack of the backdoor? So we can see in these tables, in the training phase, we will inject the tau with different time delays regarding to the input. And if in the training phase, we will inject the triggers to train the model using a fixed temporal position, which is 0.05 seconds. And in the testing phase, if the trigger is injected into a different positions, so we can see that the performance will degrade significantly from the 98% to lower than 5%. We can see that the performance suffers significantly under such unsynchronized scenarios that is caused by the unsynchronized or trigger position tau. So how do we address this challenge? So we propose a joint optimization scheme to learn a trigger pattern and a model simultaneously. So the objective is to make the trigger robust to any unsynchronized, to be robust to any tau. In this way, we can train a model without knowing tau in priors to launch a practical attacks. So we design a joint optimization scheme to learn the model F beta point and also the audio trigger simultaneously. And in this attack, we incorporate the trigger variations when we poisoning the model. As you can see, we randomly select the tau 1, tau 2, tau 3 for each audio sample we inject into the models so that the model will be robust to the distribution, different time distributions of the trigger delays. So in addition, we find that the human speech, if the trigger is fall into the part of human speech, the human speech will interfere with the time frequency patterns of the triggers so that we make the attack ineffective. So we also design a method to incorporate the impact of human speech. So we design an optimization function, which is taken in two parts. The trigger is for each input sample, we inject the trigger inside the speech part, which is the tau in, and also we inject the speech in the trigger in the non-speech part, which is the tau out. In this way, we can balance to learn a same unified and same representations of these two triggers. So if they have the result in the same representations, for example, the Z beta with the trigger inside and outside of it, we can make the model and also the triggers robust under the impact of speech, human speech. In addition, we design our final goal is to replace the audio triggers to impact and audio sensing systems. So we need the trigger to be imperceptible to human being. Otherwise, the human will notice our attacks. So our way is to carve the trigger with similar to environment sounds, such as bird chirps or engine sounds or some footsteps. So the sounds that are similar to the user's environment sounds. And we optimize the triggers in this way by using the mean square errors and make it similar to a voice template of environment sound. In addition, we also incorporate to simulate the over-the-air distortion when we generate the trigger patterns by using room impulse response to make it robust to the over-air distortion when the audio trigger is propagating through the air. So we conduct extensive experiments to evaluate our attacks by using different machine learning models, including CNN-based, IM-based, and ResNet. And also we evaluate our attack by using different speaker recognition model, including widely used X vector and also DSpeaker and SciNet. We evaluate our attack by using different data sets. For speech comment, we use the Google speech comment dataset, which is a benchmark for speech recognition. And also for the speaker recognition, we use VCDK dataset for speaker recognitions. And there are 30 class for speech recognition and 100 class for speaker recognitions. So To evaluate our attack performance, we use two metrics. The first, the CA, means that the clean classification accuracy, where the trigger is not present in the audio input. We just want to see how the model behaves under clean data. And also we have, and in this case, we can see that before and after we applying our backdoor attack, the model's performance, it does not change greatly, which means that it's hard to identify a model that is injected with the backdoor or without the backdoor by just seeing its clean data classification accuracy. And also we show the attack success rate, which is how likely our attack will be success if we inject the audio trigger patterns. And we also show the standard deviation, which means that if we change the position of the trigger, what is how the attack performance will suffer. So we can see that there's only less than 1% standard deviation change when we vary the position of the triggers, which means that our trigger is the trigger can be injected into any position of the audio input for the attack. So we also conduct a real-world study to investigate whether our attack is realistic in real-world scenario. So we conduct experiments by using a loudspeaker as the sound source, and we use microphones as the receivers. So in this case, the user will issue voice comments, and at the same time, we use the loudspeaker to replace our audio triggers along with the human speech, and we want to see whether our attack can success. So here is that this figure shows that the audio trigger is replaced by using 3 different sound volume from low to high. And we can see that even with a very low sound volume of 555 dB of the trigger, our attack can show almost 100% success rate in the real world scenario. So here we put together a contribution and conclude our attack. So here we study the first study the practical audio attacks that targets speaker recognition and speech recognitions. And also we generate position-independent triggers that can be injected into any position of the audio input in an unsynchronized fashions. We also deploy our triggers design our trigger by using a joint optimization scheme to jointly optimize the model and also the trigger to launch the backdoor attack. And we also demonstrate our attack is effective in both audio, in both digital and the physical domain. We demonstrate it through real-world experiments. So that's all for the for this presentation. Any question? Hi.
Have you studied any way to kind of detect this manipulation of the model, that could any way to kind of test the model or something that could
yes.
manipulated?
Yes. That's what we are working on an ongoing project. So there's maybe 2 ways we can do this, because the root cause of such attack is that for machine learning model, we are difficult to check whether some input are manipulated and some input are not. So even for some human, even we listen onto the audio, sometimes we do not notice it. So we may use even sometimes we call the non-parametrics to cluster the input data into different clusters. So in this way, we inspect some input. If some of the input that are outliers, for example, for a specific lab, there are some input that are outside the distribution of this class, then it could be an outlier, and it could be an adversary inject backdoor into the models. That is one way. And also, we may also check the model through some post trainings. So after the model has been trained, for example, distributed users. So we can also feed specific inputs into the model and check its output to see if there are any malicious patterns inside of it. That is another way. So one is prior checking, one is post checking. Both ways, I think they have potential to detect such backdoor.
any other comment?
Yeah, I'm really curious about the latest sort of example here, and very unfortunately high about that success rate that we get back. But
Yes.
would you expect it to be sort of similar with that under application? Now it's application for audio.
Yeah. So Backdoor attack have also been used in the study in different domains, for example, image domain, and also recent studies show that it is effective against cloud point and even reader. So I think the key is that it should be applicable to machine learning models because there's many applications they use using machine learning model. So the attacker's objective is that it can design specific trigger that is hidden to human. So the human cannot perceive it, but it is perceivable to, it can be identified by the machine learning models. So that is how the attacker want to launch such an attack, so that they will modify, they can find some trigger patterns. For example, in image domain, it can be just a watermark. And in the 3D cloud point, for example, for a LiDAR system, it can be an object, for example, some type of with specific shape, object with specific shape. And audio domain, we have this audio trigger, which is a short audio trigger. So it can be generalized to different domain based on machine learning model. So that's the background.